final video, we're just going to talk a little bit about path coefficients. This isn't going to be too long, and we can revisit this also when we are together. All right, so path coefficients have a lot to do with variance, covariance, and correlation. Hopefully none of those things sound too scary to you. This next slide is going to say recall. You guys probably will not be recalling this, and we can also talk about this more when we get together. All right. Okay, so this is a lot of math to throw at you all, but we can take this step by step. So this is just a definition of the variance, which is basically equal to the standard deviation squared. And then we've got the covariance. So this is just the definition of covariance, right? Which is the sum of every value of x minus the mean of x times every value of y minus, or the sum of every value of y minus the mean of y divided by sample size minus 1. All right, so covariance and variance. So then our variance covariance matrix is basically just telling us about the relationships between the variables in our model. So here we can think about it as sort of this matrix where we've got x1, x2, and y1, assuming those are the only variables in our model, x1, x2, y1, and then the variance has to do with x1 and x1, right? So the variance of x1, the variance of x2, and the variance of y1. And then this covariance has to do with the relationship between x1 and x2 in this case, between x1 and y1 in this case, and then here between y1 and x2. And then this is just the same, and basically the mirror of what's going on in the top triangle and the bottom triangle. We've got the covariance of x1, x2, and so on. All right, so this is the variance covariance matrix. If we're thinking about correlation, we're talking about, this is maybe something you're used to thinking a little bit more about, the correlation between a couple of variables, right? We've got the covariance divided by the standard deviation of x times the standard deviation of y. So this would be the standardized covariance matrix is based on these correlations, right? So here, the correlation between x1 and x1 is 1, right? Perfect correlation. And then here you've got the correlation between x1 and x2, between y1 and x1. So in this case, we've just got the covariance, and we are dividing it by the standard deviation essentially to standardize the covariance. So that standardize just means make the value between 0 and 1. Okay, so covariances are often used to fit models. You can think about them a little bit like slopes, and we'll talk about this more. They can be useful to think about what is the real size of the effect in terms of the units of your y variable. So what is the size of that impact of x on y? Then over here, this is when we use the standardized or the covariance, the standardized covariance matrix, or the correlations, we really use them to think about which variable or which arrow in our model is more important. This will become a little bit clearer as we go through the class. Okay, so basically over here, we're using these to think about our unstandardized path coefficients, and then these have more to do with our standardized path coefficients. So an unstandardized path coefficient, gives us an idea of the absolute strength of the pathway, of the arrow that we're looking at. So in this case, what those path coefficients mean is a 1 unit change in x is going to result in some unit change in y. So whatever that number on your arrow is, that's the unit change in y that's going to happen when you make a 1 unit change in x. And so for a standardized coefficient, what those really tell you is the relative strength of the pathway. So it's good for thinking about which of the arrows in your structural equation model is the most important arrow, or which ones are more important than others. So they're good for comparisons among pathways. The definition is not really that useful in any other sort of interpretive way, and It's defined really as a 1 standard deviation change in x results in some standard deviation change in y, so whatever that number on the path would be. So in general, unstandardized, it's good for prediction. The coefficients are in the raw units of y. They have real direct meaning, real world meaning, and they can be compared across pathways or across models that have the same units. Standardized, on the other hand, is good for ranking, looking at the importance of the various arrows in your model, but they have a lot less clear real world meaning. But they can be compared across all the pathways in your model. Okay, so path coefficients in general show, with all the other variables in the model held to their means, how much a response changes when your predictor is varied. So they're going to be the numbers on these arrows. So this is another sort of cool thing that you can do. So here we've got x1 directly impacting y1, but then indirectly affecting y2, right? So you can calculate the strength of a compound path or the strength of an indirect effect just by taking the product of the coefficients along the path. So multiply these two coefficients together, and you have the strength of the indirect effect of x1 on y2, which is pretty cool. So here the indirect effect would be 0.33. You can also get the total effect of one variable on another by adding together its direct and indirect effects. So you could get the direct effect of x1 on y2 here, right, 0.15, and then you would add it to the indirect effect of x1 on y2 through y1, right? So you would multiply 0.64 by 0.27 and then add that to 0.15, and you would have the total effect of x1 on y2. Right, so I just told you how to do that. So if you wanted to try to do that on your own really quick, or you pause it and do it, but here is that answer. Okay, so just wanted to give you a little bit of an overview of that, of path coefficients, and we'll probably talk about them a little more in class, although really the goal of the workshop is to get you guys able to code this stuff and think about how to do that. So in general, though, the path coefficient really represents the independent contribution of the predictor on your response variable. And then the indirect effects can be quantified by multiplying those compound paths. So two really cool things about SEMs. Right, and that is all.